And therefore, I look on the screen. Okay.
And whenever you're ready.
Okay, I'm ready.
All right, next we're going to go ahead with Pradip Maitra. Go ahead.
Hello, my name is Pradip Maitra, and I work for TAS and currently assigned to this New York City's ECTP program, IV&V. And you heard Mike Desmaya before me introduce the ECTP project and its overall. I am trying to focus on the radio system, and in general, I'll try to say what a PSAP radio system looks like. A PSAP radio system basically public safety answering point radio system. New York City uses the word PSAP, PSAC. Okay, now let's go to the next slide. We're getting into the details. I click on that. How can I go? So ECTP is Emergency Communication Transformation Program, and this program has been there for some time, and we are in the middle phase of it, and it is likely to get over in about another 3-4 years. And so the main project, the main emphasis of doing this ECTP project, might say, is upgrade and bring up the system to the demands of today. And so I'm going to go through these points, like you want to upgrade the PSAP 1 at downtown Brooklyn, and you want to push towards an IP-based system. The system is basically a mixture of conventional voice channel systems and IP-based. We want to push as much as possible to the IP-based system. And it is also pushing towards the APCO 25 standard. Okay, the system is also pushing towards the APCO 25 standard. The APCO standard, it also allows you to do quite a few. I mean, you can go to the APCO standard and not implement all the later features of it, but at its highest point, it is using a trunk system with very small frequency bands. So you have a very high usage of radio frequency and its resources. And of course, one of the goals of this ECTP project is to go towards greater availability, so that you have more people can actually make use of this 911 system, or in other words, you can accept more 911 calls. So let's go to the next slide. And so let's see how a PSAP system works in the first place. So there are two basic entities in the PSAP system. You see, there are the call takers and the dispatchers. Those are live human beings. They are actually taking the call, and a dispatcher is trying to arrange resource needed to actually handle that incident. So when a 911 call comes in, you get a call taker, you talk to a call taker. This call taker, he or she, what it's doing, that person is actually going through a computer triage and trying to figure out the severity of the problem. And the responsibility of the call taker is to basically attach the caller ID location and all the information related to the call, so that the dispatcher can go to the right place. So that's the first and foremost duty of the call taker, to actually make a call incident, and attach that locational information, where this call is coming from and how do I get there. Those are the things. And of course, the call is going to get recorded. for later analysis. Then the call is actually handed over to the dispatcher. Now, the call could be a fire-related incident, it could be an emergency-related incident, or it could be a police. There is a robbery going on somewhere. So, based on that type of classification, you will get over to the NYPD dispatcher or IV&V dispatcher, and there is no EMD dispatcher because EMD and FDNY. EMD stands for Emergency Medical Dispatch. EMD and FDNY, Fire Department of New York City, they are the same entity. They're not the same entity. They work from PCTV point of view. They use the same resources. So now we go to that. Now, once a call has come to the dispatcher is actually using a very sophisticated system called CAD. If you go into the internet, you will see that quite a few CAD vendors out there. That is a huge piece of software. That software is tracking a call the moment it originates and the moment it gets out of the system. So the call came in, call taker took in, the call is progressing through that whole system, and it ends up with the dispatcher, and the dispatcher is going to look at the resources that is necessary to satisfy the call, and then the call goes off the screen. That's how a 911 system works. So now, the call, that's the progress of a call. Let's see what the dispatcher needs to do at that time. The dispatcher is going to summon up the resources that he or she has. So what kind of resource can the dispatcher get through? The fire truck, the ambulance, or a police officer. How do you communicate to them? Now, they are out in the field, and the only way to communicate to them is by radio. And that's where the APCO 25 standard comes in. And the system is going towards that. The way to get to the radio it's kind of simplified in this diagram, but basically you will use sophisticated things like fiber channel and trunk lines and microwave and whatever means you have to get close to the police officer, and then ultimately through a base station radio, which in that 700, 800 megahertz range to actually talk to that officer. So that's how the system works. Now let's go to the next page. And how much time have I used? Okay, I'm almost finished. So here are some of the design details. Let me go through that quickly. So you know that the FDNY and NYPD, they share the same infrastructure, like a physical building. They have similar equipment, but they are not quite the same. They have different carrier frequencies for UHF radio, so as to say. They have different network connectivity. The system is not completely parasitic, and it's going towards it in the sense that NYPD and FDNY, they're both trying to root out as much of the conventional system as possible and go towards IP-based system. The zone controller is something I kind of thought that it might be interesting to actually get to the concept of a zone controller. A zone controller is basically the central piece of software that is taking care of one PSAP building. So you have a zone controller in PSAP building 1, and you have another zone controller in PSAP 2 building. The idea is that each one of these zone controllers should be self-sufficient and powerful enough to cover the entire call volume when one fails. The system is not just that much. It's more robust than that. You can actually kill both zone controllers, and still the system is not going to fail. It's still going to work because there is something called site controllers. The system is not likely to fail even with both zone controllers not working, believe me. And there is the other type of failure that the system is actually watching out for all the time. What happens if your audio network fails? You're talking to quite a few resources out in the field, like police officers, fire trucks, ambulances. What if that particular audio routing network fails? Can you still get to that? Yeah, there is a system called the ECS. That's the last bullet on this thing. You can actually use emergency communication system and baseband frequency to get directly to that thing. You don't have to use microwave frequency. You can use powerful transmitters and get directly to the ECS over UHF frequency. Okay. Now let's see the next slide. Slide number 5. So what is the role of NASA's IV&V in this whole thing? You see, NYPD radio is just one part of a big system. I chose NYPD radio because I work on that. But that's just one part of the system. There are about 564 radio requirements and 62 emergency communication system requirements. So it is pretty elaborate, and you think of all the ramification of those 560 plus requirements. It's an astoundingly large and complex system. Each time we get a release from the city or the person, the entity that's developing the thing, Dr. Graham, that size of the documentation is pretty huge, 130 megabytes. Like you have drawings, you have CAD drawings, you have bill of material for different areas, different things. You have huge number of PDF files related to the different products that you're getting. There are a lot of use cases. There are a lot of requirement changes, requirement association, and of course, the detailed design documents. And then there are the interface documents, ICDs. So the actual volume of that documentation is pretty big. So now this project is actually using most of the COTS system from Motorola, computer or component of the shell system from Motorola, and Northrop Grumman is the main integrator of the system. AGCS, as Mike pointed out, they're using the model-based approach to see the system to actually do, instead of going to a direct line-by-line code approach, you are actually combining a bunch of COTS systems. So it is, from that point of view, it is very easy to actually model it using high-level, national-level kind of approach. IV&V is verifying that model and also verifying the artifacts associated with that model. So in short, that's the IV&V's role in this entire picture. Can I go to the next slide? So where are we? Oh, I might finish with the time. Okay. So what is the IV&V's approach on this one? How do we do IV&V on such a massive system? We started off with a statement of work document, and we started off with the statement of works document, and that document is pretty big. We broke up that document, and of course the same thing, Northrop Grumman did, into various requirements. We checked that requirement against Northrop Grumman's requirement and made sure that we both understand the same, given that the statement of work. What else do we do? We made sure the requirements were of high quality. We went through the requirement and pointed out these requirements belong to the functional class. These requirements belong to the administrative class. These requirements belong to some kind of a infrastructure class that you need so many amps of battery power supply for that base station out there. Okay, that's something, I mean, it's hard to realize it in a piece of code. So they apply to different levels of scrutiny. So we made sure that we understand the requirements and broke those requirements up, have broken those requirements up into various categories, and each and every requirement is pretty high quality. It's not ambiguous, doesn't have multiple ramifications, get as atomic as possible, and things like that. Now, for the functional requirements, what else did we do? We actually captured the use case and their behavior. The idea is that you know that this requirement is supposed to do something. It is supposed to do something, so let's see how it does it. The use case will capture that details. And we made sure that most of the functional requirements are mapped to some use case or other, and that use case is really reflecting the behavior that's supposed to happen out of that requirement. That's one thing. Then we evaluated the design documents. We evaluated the drawings and the BOMs, the bill of materials. So how do you evaluate the design document? What you are looking for is the consistency of multiple SO requirements against the suggested design. You look for particular pictures, you look into a particular picture that says that this is how the system is supposed to work. Okay, very good. Now let's see all the components of the picture. Have they been captured in the drawing? Are they there in the BOM? Are those numbers of those components matching up against the BOMs? So this type of cross-check against the design documents and the actual drawings and the bill of materials we had to do for quite a few of those design documents, detailed design documents. Then we went to the ICDs, interface control document. An ICD is basically, you know what it means. It's basically it's specifying an interface between two different components of the system in general. So there were some ICDs available, and we made sure that the ICDs were actually covering the requirements as they should. Then what else did we do? We made a redundancy analysis to see that the viable failures are guarded against another trace. That redundancy analysis, you know, the system is designed not to fail just like that. I told you one example, the main controller. Even if one fails, there is another, and even both fail. Even if when both fail, the system will still function for a good deal of time. So that kind of consistency, that kind of redundancy is built not only into the zone controller itself, it is built into the network, into the communication system, into the base stations, into accessing one particular group of police officers or call takers and things like that. So it is highly redundant, and there are multiple paths available to reach from one point of the system to another. So we did an analysis of that path and made sure that, well, I don't see a single point of failure which is going to bring the whole system down. I mean, even if you go to a room and actually shut one particular machine down, almost nothing is going to happen. And you'll get warnings. Supervisors will see that there is a warning out there, but the system is going to fail. No way. So that kind of thing. So now that we have done some of the redundancy analysis and things like that, let me try to summarize. Let's go to the last one. Page number 7, please. You know, as our NASA project lead, Mike was talking about, that we entered into this project during the elaboration phase. And that's what this diagram basically shows, that There was a baseline phase, there was an inception phase, and then it got to the elaboration phase. What do we do in the elaboration phase? We actually try to write the design document. We try to write that drawings. We try to write that building drawings, how the connection lines pose. I mean, in the building, everything that you need to draw to actually get that system installed. That's what is being done on the elaboration phase. We do ICDs. We do bill of materials. So when we came in, we had an onslaught of documents in the range of hundreds of megabytes for each and every release. And with our systematic approach and the great direction of Mike and others, we have been able to get through the documents with flying colors. And we do have a grip on the whole process now that, okay, next time when that comes, it's going to be that big, so we can plan it beforehand and go ahead. So on the entire, for the entire project line, you can see that we are in the elaboration phase and it's almost ending that phase. We are going to go to the construction phase, and the transition phase will be the place where you actually hand over the system and user accepts it for the final time by testing it. That transition phase is probably a couple of years away still. So as usual, IV&V has supported quite a few projects this magnitude. One of the very big complex IV&V project that was highly successful was the Mars Science Laboratory project. Everyone knows about it. This New York City ECTP project is another highly complex and very big project. And with all the knowledge base and the engineering guidelines and the system approach that the IV&V provides, we are pretty sure that we will get through this project and make it a success story like everything else. Thank you. Now, I do have some time. If you go ahead, we can ask questions right away. Or so how do you want to go? Frankly speaking, that would be the job of our project leads. If Mike wants to chip in and answer that, Mike is sitting right there. Mike is the project lead on the NASA side. He can chip in and he should be able to answer it more.
Operator cannot understand you on the phone.
So I have a question on the internet. The question is, who determines the use cases and whether a failure is viable? The first responders, the network engineers, or IV&V?
Who determines the use case?
Who determines the use cases and whether a failure is viable? The first responders, the network engineers, or IV&V?
I mean, the first responders are, they probably, by use case I mean how one particular design is going to get used. It's not actually a reflection of an actual fall. First responders will come when you're actually handling a fall, I believe. Maybe I don't quite understand the question very well, but thank you, Mike. I hope that answers your question. And I think it's 11:15.
All right, if there are any further questions, we will go to the breakout session for those. And we are going to have the next question. The next presenter is presenting remotely, and it'll be just a second while I get them online. Thank you. Okay, Roman, if you're ready, can you go ahead and speak? Okay. We are ready when you are if you want to go ahead and get started.
It's not my picture, Pradip, from